So we've done a lot of this work already with that Stu Schwartz handout, so I'm not going to read this to you. Read it, make sure you understand it. There's some special, displacement is the total change of position. Very important that you know that. Positive velocity means it's going in a positive direction, whether that's up or down or left or right. And negative velocity means it's going down or left. Speed is the absolute value of the velocity. And if you're taking physics, you know that already. And the acceleration is the second derivative. Okay, and we're going to do a lot with that. You'll get familiar with it. So instead of spending a lot of time on all this text, let's jump in and do this problem. So I'm looking for the displacement, which is my total change, or Bug's total change. So what's S of 2? What's S of 1? And we're going to subtract those. Well, when I do this on my calculator, because I've done it 4 times incorrectly, negative 16 times 4, because remember we're substituting in 2 for this t. So negative 16 times 4 plus 32 plus 320, I'm getting 288 feet. So that's where it is. He's down at 288 feet. As S of 1, I'm going to substitute in 1 here, and negative 16 times 1 plus 16 times 1 cancels out. I'm getting 320, so I'm going to subtract that. What's 320 minus 288, or 288 minus 320, really? So it's negative 32 feet. That means he's fallen 200 feet, or 32 feet in that 1 second time. So when will Bugs hit the ground? So with this one, we're looking where does S of t equal 0. So we could try to factor that. We could use quad 83, quadratic formula, quad 83. I'm going to choose to use quad 83. So let me punch that in my calculator. So A is negative 16, B is positive 16, C is 320. So my calculator is telling me t equals negative 4, t equals positive 5. Well, we aren't going backwards in time, so that negative 4 is an extraneous root. So the only place we're going to deal with it is 5. So when t equals 5, Bugs hits the ground. Okay, so now we're dealing with the velocity part of this. So velocity is the first derivative. So what is s prime of t? So remember, we're going to bring the x, it's just a power function. So I'm going to bring the exponent down, multiply by this negative 16, so negative 32t, and then remember 2 minus 1 is 1. And then this one, we're going to it's just as a linear piece, so plus 16, and then this is a constant piece, so the derivative of that is 0. Now they're asking me what's the velocity and impact. Well, we know he hits the ground at t equals 5, so it's s prime of 5. Well, let's see, 5 times negative 32 is negative 160, plus 16. So we're going to subtract those. So what is that? 50 negative 144. And then it's important to include your units, feet per second, because we're measuring s is in feet, t is measured in seconds. Notice he says what's the units. Okay, what's the speed? Well, the speed is the absolute value of the velocity, so his speed equals positive 144 feet per second. Then we want to find his acceleration at that time. Well, remember, acceleration is your second derivative. So the second derivative of this, or the first derivative of this, s prime of t equals, well, negative 32t is just linear, so the slope of that is negative 32, and the derivative of 16 is 0. So now what are the units? Well, we took the derivative with respect to time, so originally it was feet per second, and now we're taking the derivative of that again per second. So that's the x value, right? So feet per second squared is the unit here, and notice that this is similar, though that's just a part of this function. Won't always be this. So feet per second squared. It is the acceleration due to gravity, though, from free fall. Alrighty. So some big ideas, and again, you've seen some of this already, so this shouldn't be a surprise. This is the graph. What you got to pay attention to with here is what are you looking at? What kind of graph? And they're telling me here that this shows the velocity, so I know I'm looking at the derivative. I almost wrote inverse here. I'm looking at the derivative. And when the derivative is less than 0, it's moving, this is moving along the x-axis, so it's going left and right. And when it's less than 0, it's moving left. When the derivative is greater than 0, it's moving right. So what am I seeing here? Which way does a particle move at first? Well, it starts standing still, and then it's going negative. And even though this slope is negative and this slope is positive, we aren't looking at that. Remember, we're looking at the y values. So it's moving left, right? Because my slope is less than 0. Moving left, still moving left. Momentarily stops because my velocity is 0. And then it's moving left. Then it turns around right here at, what is that, 1, 2, 3, 4, 5, 6, 7. So at t equals 7 is when it reverses directions and starts going right. I know that because the y's turn positive. So let's answer some of these questions. Which way does it move first? Left, because f prime of x is less than 0. When does the particle stop? Well, it stops when the velocity is 0, when it hits the x-axis. So momentarily, I mean just an instant in time, it stops at t equals 3, and then it stops again at 1, 2, 3, 4 at t equals 7, and then it stops again at the end. I mean, I guess we could worry about the initially stop by stopping there, but I don't know if it works well to talk about the initial. But I am going to say at, let's see, 10, at t equals 10, it stops again. So when does it change direction? It changes direction at one of the zeros, and when the derivative, remember this folks, this is important, when the derivative changes from a negative to a positive, the function's changing directions. Conversely, when it changes from a positive to a negative, it's changing directions. But right there is when it changes direction at t equals 7. And when is it moving left? It's moving left on that open interval, and it is open because right there at t equals 0, it stopped. So it's moving left from 0 until 7, and again it stopped at 7, which what's you're going to have happen to you sometimes is that these graphs are going to start, like at t equals 0, it'll start like this. So that tells me at time equals 0, it's already moving right because it's a positive value at t equals 0. Okay, whereas this one is at t equals 0, the velocity is 0, so it's not moving at all at t equals 0. Let's see, particles moving right. Let's see, it is moving right at, let's see, from 7 until 10. And when is it speeding up? So now, you've done some of this already. Let's see if I can erase some of this. Okay. So it's speeding up when the velocity has the same sign as its slope, whereas the second derivative. So if the first derivative, mathematically, we're trying to compare the first derivative and the second derivative, and when those are the same sign, it's speeding up because it's not fighting each other. Remember, we talked about the ball getting thrown up in the air, how and at that moment in time when it's at its peak, it's not moving at all, it's hanging. So it starts off getting thrown up or thrown in the air, and the speed is decreasing until it hangs at that minute in time. The velocity is positive because it's moving up, but the acceleration due to gravity is negative because it's pulling against it to go down. And then when the ball starts coming down, it's speeding up because the velocity is negative because it's decreasing, the slope is negative, and it's getting pulled down. Okay, So when's the ball speeding up? Well, all right, let me get a marker going here. I see a negative slope and negative y values there and there. So it's speeding up there. And then I see there it's slowing down because, and actually we know that because it's going, the velocity is approaching 0. Okay, here it's speeding up because the slope is positive and it's going up. So when is it speeding up? It is speeding up from 0 until 1, and then from 3 until 4, and then from 7 until 9. And when is it slowing down? All those other places. It's slowing down when the slope of these line segments is positive or negative, but the y values are the opposite sign. So right here where I put this blue, let's see, let me see if I can't delete some of this. Okay, so here I see a positive slope but negative y values. Here I see positive slope and negative y values. Here I'm seeing negative slope and positive y values. So those are places where this curve is slowing down, or the particle slowing down. So from 1 until 3, and from 5, 6, 7. So from 5 until 7, and then from 9 until 10. Notice it's skipping in between these, though this one's a little weird, right? That's where the velocity is constant. So let's answer that question. When's a particle moving at its constant speed? Between 3 and 4. Or is it 4 and 5? Between 4 and 5, sorry about that. When is the particle moving its fastest? Well, that's when the velocity is well, or when the speed is the biggest. So here I'm seeing 1, 2, 3, 4. That's a velocity of -4. So the speed would be +4, and that's bigger than up here. So it's moving fastest between, let's see, 1, 2, 3, 4, and 5. 4 and 5. I almost wrote 5 and 6. Okay, then the last little piece, what do they want us to do? Graph the acceleration. So I'm seeing a slope of, let's see, so here I'm seeing a slope of -1 between 0 and 1. So I'm going to put, let me go to red ink. That's -1. Then between 1 and 3, I'm seeing a slope of +1/2. So right about there. Then here I'm seeing a slope of, let's see, what is that, down 4, and that's between 4 and 5. So -4 between 4 and 5. Or between 3 and 5. 3 and 4, boy, I'm messing that up. Between 4 and 5, the slope is 0, because that's a constant slope, right? Then between, let's see, so from 6, 7, 8, I'm seeing a slope of +2. 6, 7, 8. And then I'm seeing a slope of 1 between 8 and 9. then I'm seeing a slope of -3 between 9 and 10. And that's the graph of the acceleration for these line segments. Now to graph the speed, remember speed is just the absolute value of the velocity, so I'm going to graph, all I'm going to do is every place this is a negative y value, I'm just going to reflect it around the x-axis. So there, 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 and it goes what, up to 4? 1, 2, 3, 4. Then it's constant for a minute, and then it decreases by -2, so down 2 over 1, down 2 over 1, and then this is all positive, so where are we at here? I think it's here, I think it's here, I think it's here. So this is what I'm thinking the speed looks like. Okay? So for this problem, we're talking about, let's see, to draw a tangent line on that point below. So here's that tangent line, looks something like this. And how do I get the slope of that tangent line? Well, given by, let's see, well, this is a function that's called p of x. So the derivative is given by, the slope of the tangent line is given by the derivative of the function, and the slope of a line is given by the rise over the run. What are we looking for? Right. I guess so. Change in y over the change in x. And all they're telling us is if you go really close, if I went 1 unit over from that and I found that point there, I could find the slope of that line, and that would be an approximation of the derivative at that point here. Okay, something you've been doing now for a while. And then they give us some definitions. Marginal cost. Let's see, so marginal cost is the approximate cost of just one more item. So that's this idea, where you're going to find just one more of it and then find the slope between the line. And then the marginal revenue is same idea. What's the difference between just adding one more thing? And then the marginal cost is the marginal profit. Oh, you subtract those, right? Okay. We can also do this with derivatives. If they ask us this, you'll see that sometimes it makes more sense to do the derivative than this approximation. Okay, so now here we go with this. What's the current daily cost? Well, that's just asking us to find f of 40, right? Because they're telling us there's 40 radios produced daily. So what's f of 40? Well, I've done this with you before, but I thought I'd take a picture of this. So on my calculator, and yes, I'm just using an old 83 here, I typed in 40 and I hit enter. And then what I did, just so I can save myself some steps later on, I typed in the coefficients. See, I typed in the 0.02, and then I did second answer to the third times 0.1 times the answer to the second plus 42 times the answer plus 300, and that's that value. Okay, and this is where using that answer feature is so nice. I typed in 40, hit enter, and then I just hit second enter a couple of times to pull this back up. I hit enter, and there's that number. So that's what that is, the plus one more. So it was 41. So we had 40, and I added one more to it, and then so we got that answer. And then that would be part B. And then how do I get the marginal cost? Well, I'm going to subtract the two numbers. And when I did that, I got 59. So let's see. Let me write that down. So I got. I deleted my first one. Oh, the first one is 22. 68. So that's what f of 40 was. So f of 40, or f of 41, right here, minus 2268, gave me 59.94 if I round, because it's money. So that's the cost of producing that one more unit. So for this next problem, number 5, I decided to try tackle it a little bit different way. I threw the equation into my y1 function, quit that screen, and then if I'm looking for the marginal cost of producing the 11th unit, I want to find C of 11 and then subtract C of 10, and that'll be my marginal cost. And notice that's exactly what I did here on my calculator. So that's the marginal cost, dollars per unit. This last page, we've already done this in section 2, so I don't know that you really need to worry about it. It'd be good to remind you. Remember what we did is I gave it that program nderiv, which dumps in y2. It puts what he has here, and then it also does it for it does it in y2. Okay, so don't worry about these two things. You know how to do that already. So hope this helps you and is better than Mr. Leakey, I think, maybe.